thank you, GitHub, for hosting here. Thank you, Encore, for putting this together. My name's Kevin. I'm a founding engineer at Dexterity. And I'm just really delighted to get a chance to share some stuff with you guys today. So I want to start with just a bit of a background on Dexterity, who we are, what we're doing, just kind of set the stage. So Dexterity is a robotics company, and we're building a hardware, software, AI platform to really unlock the value of physical AI for all kinds of real-world tasks in the warehouse and ultimately beyond. A little bit of by the numbers, we team of about over 200 people, been in production for quite some time, working with really customers who are leaders in their own domain, in their vertical. Some of these names you might recognize, FedEx, UPS, might have your packages shipped through them. But what do I mean by, I guess, a platform for us? So the easiest way I can describe this is with the smartphone analogy. So there's the hardware, the actual physical device, the phone that you have in your pocket, the operating system, iOS, Android, that kind of provides abstractions and a framework to interact with those physical capabilities, and then applications on top of that OS that really strive to understand the user's need and provide some value in the final solution. So similarly for Dexterity, there is the physical product, so the hardware that we provide, which you get a little sneak peek of here, officially launching in a bit, which has multiple arms, camera, the roving platform to just go here. A little platform to kind of roam around. On top of that, their equivalent of the operating system is this Dex AI software platform, which provides these bundles of robotic capabilities as skills. And at the top layer, the applications, which again leverage the capabilities of the Dex AI, of that platform, to unlock value for actual end customers. And so some of the skills here that are offered by the Dex AI platform, you can see in this little collage. And these are all bundles of perception and motion and control that can be stitched together to really unlock applications in the warehouse. And for us, some of the main applications that we've been spending our own time and energy on and looking at are in truck loading, unloading, palletizing, depalletizing, order building. These are things that are pretty universal throughout the warehousing space. But there's more. Like there are more applications for to do with these robots with the mech platform, and they're not all that we're going to do ourselves. And so we do intend to sort of open this up to further third-party developers. It's kind of in early stages, but the kind of first partners are already underway. And so with the mech hardware, the Dex AI sort of software platform layer and these applications, we really are trying to bring physical AI to bear on some of these hard tasks in the warehouse, in the real world. And I've mentioned, I guess, physical AI a few times. I just want to clarify exactly what I mean when I'm saying that here, which is a model or a system of models that has a diverse set of multimodal input, images, video, in our case also force sensor data, pressure sensor data, maybe audio, sensor data of the agent's own embodiment. So where is my arm in space? How fast is it moving? This understanding of self and a way to ingest goals and tasks to accomplish in the physical world. And internally, a system that's actually building a model of how the physical world works, either implicitly or explicitly, understanding entities and how they are interacting, their approximate dynamics, and again, a sense of self. And critically, on the output side, being able to either convey the understanding to humans through language or images or otherwise, but also critically to actually control actuators and make some physical change in the world. This is, I mean, the thing that is super valuable in the warehouse is to actually like move things around, not just understand, but also do. So physical AI for us is sensing, perceiving the world around us, making sense of the world around us, and then actually taking action and interacting, touching the world. So that's great, but how can we actually take physical AI and bring it to bear on some of our customers' thorniest, biggest problems? So FedEx came to us with the need to automate truck loading. And if you look at truck loading as a whole, it's like this big, thorny, messy problem. They had been unable to really automate it for quite some time. And it seems like, yes, there's some version of physical AI that should be able to help tackle this problem. But to really get there, we had to kind of decompose it a little bit and think about the space a bit more methodically. And so one axis that we can use to sort of like look at the space of physical AI is the time horizon of the tasks that we're tackling. So in all cases, using the sensory data and the actuators to, sense to perceive the world and make change in it, but the nature and the granularity of the physical understanding that is useful for some of these tasks can vary greatly. So think of on the far side of the spectrum with the short horizon of tasks, we're doing things that are more like dexterous manipulation, more squeezing, tucking, pulling, things that just have a lot of rich interaction with the world. And on the long horizon side of things, we're doing things like planning and reasoning. So something like stacking a set of chairs when we clean up from this event, or assembling the piece of IKEA furniture that you got, or tidying the kitchen. These also require sort of physical understanding, but it feels like a different nature than what you're using when doing things like putting some thread through the eye of a needle. And so these aren't entirely disjoint. In fact, to do a lot of the longer term planning, it's really helpful to have a sense of how I or any system can accomplish some short horizon task. And it can actually lead to sort of better long-term planning. And so I want to talk through a couple of examples that are problems that we're tackling at Dexterity that are in these parts of this space, on the short horizon side and on the long horizon side, and things that enabled us to really tackle the truck loading problem for this customer. So the examples that I want to talk about are tight packing, or how do I quickly and robustly squeeze a box into a tight gap, and 3D bin packing, or how do I build a dense and stable arrangement of boxes, in this case also in a truck. Why do these matter for FedEx or any customer that ships boxes in a truck? The cost of transportation is one of the major costs, and therefore minimizing the amount of empty space, not shipping air, is really important. And also, having things tightly packed actually increases the friction between packages and lets you, actually stabilizes the whole assembly. So your box that you ship isn't actually tumbling through the truck as it's driving through the mountains. And as I mentioned, the 3D bin packing here is an example of the longer horizon planning and reasoning task. Tight packing here, shorter horizon, more dexterous manipulation. So let's zoom into tight packing. Seems easy enough to put a box in a gap, right? In a tight gap. I mean, at least for us humans, we do this pretty naturally. But some of the key challenges here are that, yes, the mech has a force sensor, but the boxes themselves are deformable. They might droop. The suction cups that are between the sensor and the box are compliant. And so the signal, the force signal that you actually get is not entirely straightforward to make sense of. It's affected by all these things. And yes, there are cameras. The robot can kind of see what's going on, but often there's heavy occlusion from either the arms or the gripper, especially for smaller boxes. The scene around the place where you're trying to pack the box can also shift. It's not rigid. Things can tilt, they can compress. This is sometimes desirable, sometimes not. The weight and the surface materials of the box can differ from package to package, and the robot needs to be able to work well in all those cases. And speed is critical. It's not enough to just do this well, it has to be done fast. And so on the Dexterity platform, we can look at some of the inputs that are available to tackle this. So one is the force and torque sensor data. Another is the set of RGB images and depth sensor data that comes from the cameras on board. The history of the trajectory that the robot arm went through to this point in time. And the goal and starting location. Like, what is it that we're actually trying to do? Where should this box go? And the output is some form of control to the robot arm to decide where it should move in the space to try to achieve that goal. And so one way you might approach this is to take all of this history input of all of these different modalities and feed it through a transformer to ingest the context. Based on that context, generate a short trajectory that can then be fed into other skills in the DEX platform to achieve the task. So these other skills can do force control at a higher frequency than perhaps you can do with this other AI component. And together, this can achieve the desired effect of getting into a tight gap. And that would work, but where can we get training data? For us, there were three main sources. One is human demonstration, so teleoperating the robot to have a human show how this task can actually be achieved, and collecting the sensor data in the domain of interest. Another source is in simulation. So after bootstrapping some reasonable starting point, we can scale up the data collection much more broadly in simulation, of course, keeping in mind the fact that the gap from the simulated world to the real world will exist. And of course, real world data. So running on the mech hardware in our truck loading application out in the real world. So let's look at some examples of this in action. So here is this type packing short horizon task working on a kind of simple case that happens fairly frequently. There's a small lip, and we're packing into that little gap. Nice and easy, no big deal. However, there are more complex cases that also need to be handled by this capability. So in this case, there's multiple tiers of trying to descend into the right spot, into the target location, and you can see the mech kind of feeling its way through and trying to get the box into its final location. In this case, it's a really tight squeeze, and you have this emergent behavior of actually wiggling the box to kind of get it into the final location. Often these boxes can shift out of the way. In this case, I think they're actually quite stuck, and so this little wiggle behavior is needed to get it in. In this case, after some attempts of actually trying to squeeze the box into the gap, realizes, hey, we actually need a little more space, and therefore pushes even harder against the side boxes to see if it can shift, and you can make enough space there for the box to get into place. And this last example is one where it was actually pretty advantageous to come in at an angle to really wedge this slightly oversized box into that final location. And so with these tight packing capabilities, again, we can minimize the set of wasted space in the truck. We can have things be closer together so they're more stable as it gets shifted, at least at a single action level. But it's not enough to just place one box in a truck or place one box in a gap really well. You also have to fill the whole thing. And so the 3D bin packing task, which is the second one that I wanted to talk about, is one where the problem statement is that there's a stream of incoming boxes. Some of them are visible, some of them are not. And there is the current state of the assembly of the boxes in the truck. And at every step in time, the mech here has to make a decision as to which box it's going to pick from the visible boxes and where it's going to place it in the wall. And it has to do that repeatedly until we have a truck full of boxes. A couple of key challenges here, and maybe also opportunities, you could think of them this way. One is that it has to have an understanding of physical stability, not only for the action that it's currently executing, the box that it's currently placing, but also for how that's going to affect sort of boxes that it might want to place on top later. Second, it needs to really understand itself in a way. The agent making these decisions at the high level is going to have to use these lower level, shorter horizon AI capabilities to execute its action. It's going to have to use the tight packing capability that we just talked about to achieve some of these placements. And so part of the decision-making task is learning how to best leverage those capabilities and work around any limitations that the mech might have with reach or collisions. There's also incomplete information about the future sequence of boxes that are going to show up, and considerations for throughput, since the two arms, if you plan it right, can be moving together much of the time. The set of possible arrangements of boxes in the truck is exponential, and success is only really measured at the end of a fairly long sequence of placements. So you can determine how stable, how densely packed a region was, maybe after about 100 boxes or so. Bit of a sketch for how you might, or how we, I guess, think about this internally is the actions and the state get encoded through this state condition action encoder, and one output from here is the policy head for what you would want, what action you actually want to take in the scene, and the others can work on other auxiliary tasks around geometric properties or stability properties or feasibility properties. This is really just to help learn really useful representations without relying entirely on the kind of sparse reward at the end of the long sequence. And then on top of that, can layer some model-based planning to kind of imagine a future state that would happen for each of the actions that we can take, and really leverage the information about the boxes that we do have based on the cameras, as well as distribution information from the just history of boxes that we imagine we could have seen at this particular site. Because the required scale of data here is quite large, and because the system is trying to learn kind of higher level properties that is supposed to be robust to variations in box sequence and box properties and whatnot, we can lean pretty heavily on sim. And in simulation, you can vary a lot of the properties of the boxes, such as the coefficient friction from cardboard, the disturbances that get injected. Here we're rotating a pallet or shaking a truck a little bit to kind of simulate some possible disturbances that you might expect during the building process. And of course, in these simulated environments, we can include some of the constraints that the lower level or shorter horizon tasks have. So we can simulate the type packing capability within this environment and allow that experience to inform the higher level bin packing AI. And so those are the two tasks that I really wanted to kind of share with you all. I would say that sort of we're still really in the early days of physical AI, but that there are forms that are creating value today. That the spectrum of those tasks is really, really wide. And at Dexterity, we're tackling problems in both parts of the spectrum. And we actually think there's a lot of value in composing sort of the long horizon planning with the short horizon manipulation. And the two examples that we looked at today are with type packing, or how do I get a box into a little gap, and 3D bin packing, which is using that and using some of the other skills and other capabilities that that leverage the short horizon AI capabilities. How can we achieve this longer term goal of packing a truck densely and stably? And that allows us to really solve some really important problems for our customers, in this case, truck loading. But perhaps more importantly, we're also working on this hardware, software, and AI platform that will be open to help bring robotics and physical AI to more places where it's needed, and allow other people to really build applications on top of the device and the OS